and I'm going to talk about a specific topic. It's probably interesting for a lot of companies, which relates to one of the most familiar and popularly used Kubernetes as the container orchestration, and specifically about security concerns related to it. You can switch to, so I'm having control. Let me see.
Yes.
Okay,
Yes.
perfect. So you guys have heard a little bit about Achilles, so I will not repeat too much, just basically talking about a platform that serves all types of use cases, from secret management to key management and zero trust remote access, based on unique technology that allows the customer, the user, to have zero knowledge encryption, which means that even us as the cloud provider or the SaaS provider does not have access to the actual secrets. We are unable to decrypt them. Only the end user can. Okay. Can I switch to the next one? Let me see. Okay. So just in a few words, I know that we covered that, but just to make sure that we're all on the same page, a few words about secrets and why they're so important. Secrets are small pieces of information, digital information, that are typically used for authentication. This refers to either humans, then, for example, when you use a username and password to a specific resource, like a database or anything like that, or a web application. It can be API tokens, API keys, encryption keys, and so on. Most of the modern applications today needs to interact with another resource, right? And to do that, they would need to authenticate themselves, and therefore they would need access to secrets. The main concern about secrets is how do you protect them? In the sense that if the application, which is not a human, cannot prove or easily prove its identity, then you need to feed it with some kind of secret, which for historical reasons were part of the configuration files or even inside the code. The main concern about it is someone unauthorized will have visibility and access to those credentials, and therefore will be able to authenticate itself to the resource without anyone knowing this violation, this security violation. So protection is definitely one of the things that we want to do with secrets. But the second part, because we are talking about large number of secrets and different types of secrets and different types of users for those secrets, we also want to add another layer of management, because it's not enough to throw them in one place. You need to be able to have a clear visibility and traceability of each and every request. You want also to be able to revoke access in case there is a security violation, or in case you monitor something or one of the alerts came up. And for compliance and governance reasons, you also want to have a clear and easy to read and track audit logs for specific operations. And also, as Noel mentioned, also to be able to correlate them with the actual user, the requesting user. When I say user, they normally refer to either humans or applications, machines, and so on. So what are Kubernetes secrets, and how do they correlate to that topic? So Kubernetes is probably the most popular container orchestration tool today. It's becoming the de facto standard when it comes to modern infrastructure. It was initially published back in 2014. The official release, I think, was somewhere mid 2015 by the Google Cloud Platform as part of their GKE infrastructure. And today, all of the major cloud providers, definitely the top 5, are offering managed Kubernetes services. Other companies and other organizations are using self-hosted Kubernetes service. And as I mentioned before, it's running different kinds of application. It will need to authenticate those applications to different kinds of resources. And you need to come up with a solution on what to do and how to facilitate those applications with secrets in a secure fashion. Many applications, and as I mentioned already, are still using secrets, unfortunately, as plain text, which it makes it easier for a potential attacker or hacker to get access to them. There is a solution, an existing solution as part of the Kubernetes infrastructure to store secrets and facilitate them to application code. However, surprisingly enough, it's not much better than storing them as plain text, because in practice, they are not being encrypted. rather than a base 64 encoded, which is a computational operation that can be easily decoded without the need to use any kind of encryption key. So I think what we try to aim at the first stages, when we're talking about production environments, how can we make secrets secure? And what is secure? Secure is starting by encrypting those secrets, definitely at rest, and preferably decrypted only at the application level, meaning that at any point in time they are being encrypted, and only the application that actually uses those credentials would perform the decrypt operation and use it in order to authenticate. The main concern about encryption is in order to decrypt or encrypt any kind of value or any kind of data, specifically secrets, you would need access to an encryption key. And then the next question that comes to mind is, where do I put this encryption key, right? Because the application would need to have access, and you kind of have a chicken and an egg problem because the key by itself is something that you also need to protect and also need to secure. And a potential hacker would say, okay, so I have access to the key, now I will use the key in order to decrypt the secret. So this is known to be the secret zero problem, and there are various solutions to that. One solution is basically using a protected machine identity when it comes to machine-to-machine communication. And I'll elaborate about what is considered to be a secure machine identity. And the second example is when talking about humans to use multi-factor authentication, which is another layer that without the ability to prove access to specific resource, you will not be able to use encryption keys or secrets or of any kind. About trusted machine identities, in the cloud world, all of the cloud providers are offering machine identities as part of the infrastructure. So whenever you launch an EC2 instance, for example, in AWS, or a virtual machine in Azure or in GCP or anywhere else, basically have the ability to identify itself, get a signed token by the infrastructure that can be validated by external entities. Another example is when you're running on Kubernetes, you also have service accounts that can receive JWT tokens signed by the control plane, and then you can validate the identity of the running application or running pod. Achilles also offer another type of authentication method. We call it Achilles Universal Identity, which was invented just to solve this secret zero problem. It's basically associating an identity to a specific resource or an application in a way that cannot be used elsewhere without the platform identifying it or knowing about it. That's all fine and good. Another question that comes to mind is, what if my cluster, and this is very typical in many environments and many applications, my cluster is running different kinds of applications. Okay, it's running a database, it's running some web application, it's running some another application, and each one of those require a different set of secrets. To meet the least privilege principle, you want to grant access to specific set of secrets per application or per namespace, and that's something that is not trivial to do or not out of the box. And this is another thing that I'm going to show later on. How do we do that? So let's move to that second problem, and this is the problem of segregating access to secrets per specific pods or namespaces. And again, we want to make sure that the application will get access to a specific set of secrets. This means basically that it needs to pass the authentication phase at the beginning, and then to be authorized to specific set of secrets that it needs to have in order to perform normally. So the authentication phase is done using one of the trusted machine identities, as we discussed, but your authorization has to have another type of mechanism to the secret management platform, as we will see in a bit. The second question, or the third question that you need to ask yourself, it's fine that I have a cluster, I have different applications on that cluster, I know how to authenticate applications, and I know how to authorize them to have access to specific secrets, but who, meaning humans, which individuals will have access to my cluster, and how can I control that access? And this is what we call the problem number 3 in this case, the cluster access and management. And today, when you provision a cluster, it's normally associated with a client certificate, which defaultly is set to a long-lived certificate. Long-lived meaning that it expires after a long period of time. Normally, we're talking about months and maybe even a year. And this will allow any individual with access to this certificate to be authenticated to the control plane, to the API server, in order to perform any kind of operations there based on the permissions and roles associated with this PKI certificate. In Achilles, we know how to act as a trusted CA. Other solutions can do that as well. But the idea behind that is that you have a private key that the server trusts. And with this private key, you sign a short-lived PKI certificate, which will be used to authenticate to the cluster. The advantage about having short-lived certificate that after a short period of time, as the name implies, they will expire, and therefore you will need to regenerate a new certificate in order to continue and authenticate to the server and continue to work against it. Same goes another implementation, but so another type of implementation, but same in concept, is using short-lived temporary service account tokens. And then the same manner, you need to reissue those service account tokens in order to authenticate to the cluster. Why is it such a big advantage? Because whenever you want to revoke access, it's as simple as not allowing this user, this client, whether it's human or machine, to regenerate new certificates or regenerate new temporary access token. And because they're short-lived, they will expire after a short period of time, and you will not have access to the server. Another advantage is because you need to communicate with the secret management platform that either issues those short-lived tokens or PKI certificates, those operations are being audited. So as a bonus or as an advantage, you can also see the traceability and the ability to govern and manage all the access to the server in a single unified place. And this audit logs, by the way, can be forwarded to your existing SIEM systems. So if you're running using ELK or Splunk or any other solution, you will be able to control and monitor them and basically even build dashboards and alerts based on this information and control it in a much easy way. And I also talked about the access revocation, and this is typically to be able to prove that you're able to respond quickly in case of security incidents and revoke access to the Kubernetes cluster. Let's talk about the solution for all of the things that I mentioned before, all of the 3 problems that were discussed. So the first thing, instead of using the built-in Kubernetes secret store, which has its limitations, we want to use a secret management platform that protects, meaning encrypting secrets, and they are being decrypted at application level. Also, to have controlled access to the cluster. In addition, instead of using a token or an initial secret or a key in order to authenticate to that secret management platform, use a trusted machine identity in a way that it cannot be used elsewhere without us knowing that or be stolen and used by another entity. Such cases for trusted machine identities is the cloud IAM, the Achilles Universal Identity Service Accounts, and so on. There are 2 types of, 2 categories of secret management platform known today. One of them is self-deployed or self-hosted solutions that you need to have your own infrastructure to maintain them. There are advantages and disadvantages to each one, but the main or probably the obvious penalty to that you need to have a larger operation and also pay for those hosted resources to make them work properly. Specifically, if you want to maintain them highly available and scalable, so you have lots of resources running. And the second type of solution is SaaS platforms such as Achilles, but also provided by the cloud providers themselves. Again, each one with pros and cons, but I think that at least in terms of ease of use and ease of consume, SaaS platforms are much easier to use and deploy. Now I want to show you a quick demo. I'll share my screen. Oh, I need access, Lior, to share my screen. Okay, I have it now. Thanks. And I want to take you very quickly to my terminal. Just to show you, I have like a small Kubernetes cluster here that have some pods here running. And in order to use secrets using the Kubernetes secret mechanism, you need to create a secret initially in the secret store, and then to consume it using a specific annotation. It can either be using environment variables or mounted file system. I've created a dummy deployment, and this is the file here. And this dummy deployment is basically running a pod with a single container based on Alpine very minimal Linux version. And as you can see here, we have annotation. This annotation is going to be read by a mutating webhook that you see it here, a sidecar container that is provided by Achilles, by the secret management solution. And this annotation can be done in one of two ways, either to inject a file. I'm showing the two ways in a single deployment, even though you can also use just one. So in this case, you have injected file system, a secret called secret1 and residing in this specific folder. So this is one way of doing that. And the second one is defining an environment variable. And instead of the value, which should be the actual value of the environment variable, we put an annotation starting with Achilles column and then the full path to the secret. Okay. So if I switch very quickly to my account here, we will be able to see that I have those two secrets there inside the Kubernetes cluster. And here they are, secret 1 and secret 2. Once I deploy it, and I'm using, by the way, AWS IAM in order to authenticate my cluster, right? Because I'm running on EC2 instance. Once I deploy it, for example, then you will be able to see that I have this test pod running, right? And I will use the logs to show the STD out of that specific pod. And then you can see that the first secret value, this is actually the string coming from the secret management platform, and this is the second value. As you can see, if I try to decrypt it using the web UI interface, right? So you see the secret value here. In addition, I can also very quickly switch to the audit logs and see that there were two get secret value requests. Both we were using Kubernetes AWS.
Ori, I'm sorry to interrupt. Ori,
Yeah,
I'm sorry to interrupt. People are saying that we are still seeing the login page. Are you switched to another screen?
Yes, I have switched, and
okay, so we can see just the login, presentation with your email and passwords.
So let me try to pause very quickly and reshare.
Okay.
Thank you for letting me know. Let's see if it revives itself. Do you see anything now? Or still in the login screen?
Yeah, still in the login screen.
Okay. Let me try to stop sharing and resharing, and hopefully this will solve itself. Meanwhile, I'll explain that verbally until this screen restores. Hopefully this will be done in the next few seconds. In the audit logs, you basically see the requests done by the application pod, and you see also the secret name that was requested and the entity that requested it, including the IP address. A little bit about the mechanisms behind it to allow this work to be done. So there is a sidecar container, right? A mutating webhook that receives events whenever pods, application pods are being launched. Whenever we see this application pod being launched, we look for specific annotations, and based on that, assuming that we have access to those secrets and assuming the annotations are enabled, we inject an init container to this application pod that receives an initial token, a one-time temporary token with access to those specific secrets. This init container is also the one responsible to perform the environment variable injection, as well as the mounted file system. So the actual pod, the actual annotation pod running within the same, the container that running within the same application pod will be able to consume them in a seamless manner. When I'm saying seamless, I'm referring to the fact that the application pod is not aware that there is another secret management platform serving it. Okay, it does not require any SDK integration or any kind of modification to configuration file. For this pod, it's simply receiving the secrets. Okay, I see that you took over. Yeah.
Yes, yes. There is some problem with the sharing.
Okay.
Do you want to
is
try
it on
again?
your side or on my side? Yeah, I want to try again, but right now it looks like I cannot share.
Okay, if you want to, now you can.
Let me see. Yes, let me see now. Is it any better? Still unable to see?
No, no, we cannot see.
Do you see a black screen or something? What do you see?
Nothing.
Nothing. I see. Okay, so I'll use the time to answer questions if there are any. Let's see if this is sorted out. I see a question from Ido, right? How do you protect private master key inside the key management platform? The master key, CA, private key, this is an excellent question. And this is one of the reasons why it's not so simple to implement by other platforms. There is a chicken, it's not like a chicken and egg problem, like there is a bootstrap problem to protect the initial key. And because of our unique technology, because of the DFC technology, our keys, our encryption keys are never residing as a whole at any point in time, not even in memory. So when we create a key, we basically create fragments in different geographic locations, different environments. And this patented technology allows us to perform cryptographic operations without combining them. So the traditional case is that you have a key in a single place. You need to store it in an HSM, or you need to store it in a protected device that will not allow others to access them. But if they're not existing at any point in time, then there is pretty much nothing to protect. It requires some, I know it's not, it sounds like hand waving, but it requires some understanding about how the technology works. But this is actually replacing the traditional HSM, and we can act as a virtual HSM ourselves. And with that, the key is in the most protected way, because there is no single place that you can hack into and grab a hold of that key. Hopefully this answers. Let me see if
I can see another question, Ori, that was in the beginning of the meetup. It would be great if you show differentiation in approach in regards to key clock and other solution.
So I'm not sure I understand the question. Keyclock as an IDP. What is the specific questions about Keyclock?
So I think Keyclock as a key repository secret management.
As far as I know, Keyclock is a vendor, an open source solution for identity provider. It allows both XAML and OpenID authentication methods. The Achilles platform is able to interact or integrate with any IDP, any external IDP, whether it's Okta, Keyclock, Auth0, anything like that, ping identity, and basically authenticate clients without the need for us as a platform to manage the users in two different places, right? So you continue to use your own IDP. We use this identity based on protocols like SAML and OpenID to connect you to the platform, because we have a trusted entity, trusted application that knows how to validate the authenticity of the user. I hope this covers it, but if I missed the question, please let me know.
I think it does. Guys, if you have any questions to Ori, please feel free to write them down in the chat. If you have any questions to maybe others lectures, please write them down. Feel free.
Okay, so another question, what's better to use HashiCorp Vault, which is the de facto common external secret management solution, or native from the cloud providers? work with secrets, or maybe advice, case study. Okay, so the question is basically, let's call it a centralized secret management solution. Could be HashiCorp Vault, which is one of our competitors, of course, versus using the cloud native. The one that I'm thinking about is the cloud native are typically closed garden in the sense that they work very well inside their own infrastructure. But if you want to work on multi-cloud or hybrid environment, this is much harder to do. It's possible, but it's much harder to do. And if you want to have a unified environment in access to secrets all in one place, then the recommended approach is to use some centralized and unified secret management store. Another difference is the how complex it is to set up a production grade environment versus to use SaaS services like the cloud providers. With HashiCorp Vault, I mean, you do need to have your own resources running them. You do need to make it highly available. And with the enterprise offering that allows you to have multi-tenancy and multiple clusters that will allow you cross-region replications and so on, this is also becoming very costly. So you need to also to make sure that all of your production needs are being addressed. So it's not just enough to spin up a single instance running this secret management, because if it fails, your entire workload is unable to perform its operation because there is no access to secrets, and not humans and not machines can connect to it. So you need to make sure it's highly available. You need to make sure it's scalable. It knows how to scale as a result of your workload and demands. And you need to make sure, in case you're a global organization, that it's also supporting cross-region access.
Okay. Okay, thank you for that, Ori. Guys,